Hey, Terrence and Mosh, how are you doing today?
Good. How are you?
Doing well. So,
Mhm.
so we made it all the way to the end of this thing. This is the last session.
Yeah.
And have you spoken with Wen Chang recently, Mosh? Because he's scheduled to start the machine learning and production class on Wednesday of next week.
Yeah, I'm sure he'll be ready.
Okay.
I talk to Wen Cheng almost every day.
Oh, good. Uh-huh.
Through this, we've become very close friends,
Mhm.
working with jobs and projects and all sorts of things.
That's
And
great.
he's my resource, and I'm at a point where for any big engagements, I'm not going anywhere without Wen Cheng, and vice versa. And so yes, he's ready. He's looking forward to it.
That's terrific. I'm looking forward to it too.
Yeah, and I'll be there with him too. So
Mhm.
it will just between you, me, and Wen Cheng. I think we're going to be fine. Just a couple of things on, and I haven't talked to him about this specifically. I've been in a number of conferences these last 2 weeks. Like there were two that Andrew Ning spoke at last week. There were a couple of more this week. One's going on the ODSC. Had some friends do some sessions there, and it is my big takeaway from all this is, I think we mentioned it the last session as well. It is all about operationalizing solutions, building those pipelines. Just, it doesn't matter what stack you use, you just got to get it to work.
Yeah. Yeah.
The work that I did at KPMG, I had one of those big operationalization components to it for this ecosystem of that we had worked on. I'm very protective, even though I don't work there anymore, of their intellectual property, of the firm's intellectual property. They came out, they even presented, and they opened it up. They spilled all the beans in one of these conferences. The whole thing, and everybody is doing that, including IBM and so on, trying to show people under the covers, say, look, we have this full end-to-end stack. Everything from the data, setting up the data lakes, to the data strategy and data governance and all that. We can do this with these tools, and these are all Python based, whatever, these tools that they've built. But that's because so too does what I hear when it comes to that kind of analyzing data governance. You're better off with Google. Google Analytics seems to be very much best of breed. And I haven't played with it in a good bit of time. And then to build out the operationalization, that part of it, building out those pipelines, there are so many methods where you can use the Pythonic pipelines, scikit-learn, and all of that. And then you use Jenkins and Prometheus. These are packaged components with Docker containers and so on. And you can productionalize it. And then you model management, data management, everything. And the code in GitHub. This is how you put it all together. Everyone's done different variations of it. And there's so many companies that seem to have their own flavor of how they do it, but best of breed. TensorFlow extended. TensorFlow extended.
Wow. So we bet on the right horse, right? With Sharon's book, huh?
Indeed. I think we bet on the right horse, but let's get deep into it quickly, because I think that is far, far more important. And then, because it to me, it's like data science, the hype cycle's over. Now it's real subject matter experts who are focused on, who know something about their domain, whether that be marketing or research and development in a particular academic or something field or something. Those folks are able to leverage these platforms to build stuff, right?
Yeah. So are you saying that the large companies like KPMG are doing this in droves? They're making their tech stack transparent to everybody?
They presented it today.
Wow.
There's one principal, he presented it, and yesterday, not today,
Oh, yesterday.
um, I was just floored. I mean, this was stuff that would never, I wish, I want to talk about it and mention it, but those were it's private IP.
What was the session yesterday?
It may be available. It's a ODSC.
Oh, okay.
East Boston Conference. It's ongoing right now, and at some point it'll probably be out. There were also technical VPs at IBM, who one of them, he had like twice as long, over an hour session where he walked through end to end using Watson, the platform. And Watson is over-engineered and pretty easy to use. If you've used Azure Machine Learning Studio with the drag and drop, it's almost as easy, but Watson is more full-featured. And they're able to do, for IBM Watson, it's federated machine learning. So it's a way to do things more scalably.
I see this talk that says a look at deploying and operationalizing data science models with IBM.
Mm-hmm.
Is that the one?
That's the one. The guy was a VP, right? Senior VP.
Distinguished engineer and chief data scientist, John Thomas.
Not that one. Not that one.
Okay.
There's another one. I missed that one.
And I know Oracle's new offerings. I know most people don't even know Oracle's in this space. They have an end-to-end all with the database,
Mm-hmm. Yeah.
Which is neat.
Go ahead.
No. That's all I was going to say. Everything is deployed in the database. So you already have databases containing your information. Now you run, the machine learning models in the database, you deploy it there, you hit it the same way you hit a database today.
Yeah.
Most applications can do that. So it's neat.
Yeah.
I think Spark, Spark does that. It has a way of handling big data and databases and so on that's built into it, and so you can build machine learning pipelines that access big data and do it in a concurrent, parallelized way with workers on different clusters or different parallel workers that are doing this. They're not necessarily all in the same place, and they're all it farms out the work to all of those workers and then brings it back together. And yeah. Oh, I see this guy, Kirk Bourne, who's a former astronomer or astrophysicist, and now he works at Booz Allen Hamilton.
Yeah, he's everywhere.
Yeah.
He doesn't get very technical at all. I found there are some companies, Virtu, which is run by Manasi. She did her PhD at MIT, and she's a brilliant speaker and communicator, and she's able to get some really, really good friends and her platforms in production at S&P and so on. She's done a really good job with their platform. There are companies like Saturn Cloud now, and I say this only because I have a number of friends there. Saturn Cloud with Dask has done very well. The guy who I think who founded Saturn Cloud is this Australian fellow. He's a big guy, very gregarious. He did all those podcasts on, I think it was the learning company, Data Camps or something.
Yeah, Data Camp is
one.
Yeah.
Yeah. So that one, he had a very good podcast while he had it. But anyway, he runs Saturn Cloud, and everything they're doing is quite brilliant as far as being able to operational, just having the full end-to-end platform that's easy to use, that's open source. And of course, H2O has done a fantastic job. There are smaller entities like Dot Data that have some great strengths in the data normalization, just data synthesis, data analytic, just getting the data analytic ready in order to build and productionalize something. And then you can still use their platform. Yeah, there's so many companies. The reason why we're all hearing about them as they come out is because the business realities are really what's bubbling to the surface. None of these companies are able, they're making some money, but they're not making a lot of money. Because the customers, the companies that can actually, who need to transform, they don't have the money to transform. They just don't have the money to spend and burn on consultants. So I anticipate the industry, the machine learning, AI industry, there'll be a shakeup. There'll be a big shakeup. And I suspect the winners are going to be ultimately the cloud platform providers.
Yeah.
Even though,
sorry, go ahead.
Just one point, even though AWS is like 8 times the size of Microsoft Azure, there'll be Azure, AWS, Google. Those will really be the winners, at least in North America.
Is Paperspace in that mix, or are they not quite at the level of the 3 that you just mentioned?
My opinion, strictly my opinion, so I'll give you the caveat, I don't think so. Mm-hmm. I don't think Paperspace, because Paperspace does a very specific thing. I think what Paperspace does in being able to behind the scenes have all these containers and give you all this processing capability and so on, couldn't you effectively get the same thing with Google Colab?
Yes, I believe you're right. Paperspace originally was a paid service, and then I guess they were looking behind them and they saw Google Cloud, and they said, well, we better compete with them. So they made I forget what, they branched off a piece of their business and they gave it a name, and I can't remember what it's called now. Graph Flow or something. Yeah. Anyway, they made that free. They made that part free, so you could access the compute and storage, a certain amount of that for free. And then if you wanted something more, then you would go to their paid service. So yeah, it's similar, but so it's like Google Colab, but it's nicer. Well, but it's much nicer than Google Cloud and Azure and AWS, because you don't have that complicated dashboard with all the confusing controls, and that's the difference.
Yes, that the portal, every one of them, whether it's the AWS portal or the Azure portal or GCPs, yes, you're going to have that, but you have to get better at, I think we all have to get better at knowing how to use that, knowing which services to spin off at any given time, and how to do it cost effectively. Think less like an engineer and more like a CFO.
Yeah, I mean, my feeling is that it's not on us to do that. It's on them to do that. It's on them to make us an interface that just has what we want in it and that we can control easily. Like, because just like I think I mentioned this to you a couple of weeks ago, I dipped my toe into AWS and I spun up a service to do something. And then I was horrified to find out that the service was running even after I turned it off and I was being billed. So I started looking for how do you turn this off? And there's just infinite number of rabbit holes to go down. There's no clear answer to how to turn it off.
Right.
So,
yeah, and I think I said, of course they're going to charge you, and because you are, and as somebody who's had to deal with those massive bills, they're a shock when you see it.
Yeah, and this is a free market, so they're going to have to come up with a way that to do this so that people are going to actually want to come in.
Yeah.
Otherwise, if they don't do it, somebody else is going to do it and meet them to it, you know?
I don't know what to say. Yeah, I completely agree. But then it's one of those things where they're getting so much money already. Why even give up $1 or $2?
Yeah, well, like I said, it's going to be competition. That's the only way they're going to give up.
We need more competition. We need more competition, certainly. And if the competition just really boils down to just the major cloud providers, AWS, Azure, and Google. Yeah, then we're gonna all. It's not gonna be easy for everybody else. There needs to be others out there. I don't know. I don't know what.
Because I remember the early days. I don't know if you remember this. You probably do. The early days of Netscape, right? When you could the thrill of getting online and being able to explore the World Wide Web in the early '90s.
And building
in those days, in the early '90s, and you actually had to be a domain expert. You had to be able to assemble all these different pieces of code and put them together, packet drivers and this and that. And the people who did that were gods. Everybody would be at their door. Hey, yeah, help me connect, right? And so pretty soon people figured out that, if you want to get more people on board, you have to make this easier. And so they did, and that's how everything opened up.
It was Andy Jassy, I think he was even saying how he was the guy who helped Bezos launch AWS, and that was only like 15 years ago. And I remember that so vividly. Even then, it's like, okay, we've got all this compute because Amazon.com, they had something called ODBOS, is what they called it, ODIBOS. I don't know what it stands for, but they had 92% of overcapacity from what Amazon.com needed. And it was just sitting, that compute power and internet serving, web serving, whatever, was just sitting there idle. And so they said, why don't we just resell it? And they got Netflix was one of their early customers as that was being launched, because Netflix came out of they were mail order and then went to the online. Anyway, we're reminiscing, shall we?
Oh, it's good to hear.
So anyone want to dive into to the review? I think we have more on our plate than we can actually finish today. I'm going from chapters 8 through 17, or actually 8 through 19, but maybe we can just hit the highlights of each chapter and try to go quickly.
Are we going to do it with the notebook, or are we doing it via the book?
Maybe just through the book. I don't think there's time to do it through the notebook.
Okay.
So there's the dimensionality reduction techniques that are introduced in chapter 8, and so let's see, the first one he talks about is PCA, which is at least straightforward to implement, if not to actually understand. But actually, you can understand the ideas behind it fairly readily, but the matrix, the linear algebra part is not so simple. But the main idea is to find us, is to rotate your data into a space where, and find the directions where the variance is the largest, and then that means that direction will be the most important. That is a linear combination of all the other features, and that direction will be that direction is the principal component. And then I guess it turns out that when you do this kind of rotation using SVD, you automatically get it to the state where the principal components are organized and along the diagonal of the matrix. And so, the first principal component is the most important one, and then the second one is the second most important one, and so on. So they're kind of like ordered. And then you can, so once you do that, if you do that in the same with the same number of dimensions, then you can start looking at the very smallest eigenvalues and say, we can eliminate those, and so we can project down to, say we have a 100-dimensional space and we find that only like 20 of them are that important in terms of variance, in terms of accounting for the variance of the data. Maybe 20 of them, maybe 20 of the 100 features account for 95% of the variance of the data. And then you could say, well, let's just project down to a 20-dimensional space, and then that's dimensionality reduction. Instead of 100 dimensions, you now have only 20 dimensions to deal with, and that makes your problem more tractable. So that's that part, and then it's implemented in scikit-learn, and there's this command called pca.explained variance ratio that allows you to look at how much of the variance is accounted for by each of your features.
Joseph,
yeah.
Where are you? Which
I'm just looking at page 222. I don't know if you have the page numbers. Okay. I'm looking in chapter 8. If you don't have the page numbers, it's under the PCA section, under projecting down to D dimensions. And then there's a section after that called using scikit-learn. And that's where it shows the method to get, well, actually under that section is the explained variance ratio. And it shows the method pca.explained underscore variance underscore ratio underscore. That method gets you the explained variance ratio of each of the components that you're keeping. And so that's how you can decide how many dimensions you want to project out, right? So then he talks about choosing the right number of dimensions and so on. You do a plot of the explained variance ratio. That's figure 8.8-8, and then you look for the elbow in that curve. And in this case, it looks like it's at about 90% of the explained variance, and then you cut your losses there. But you go farther. I mean, the elbow is at maybe 90%, but then you go farther all the way up to looks like 95%.
Yeah.
And so now he's choosing out of 400 dimensions, he's keeping something like 150 of them. And that is all you need to account for 95% of the variance in your data. So you lose when you do that, you lose information, but it might be worth it because your model is simpler, more tractable.
Just help me understand just one point here, and this may be fairly obvious, but it's a probability and statistics question. Yes, you're only taking the arbitrarily picking a point where you're 95%, why do we pick the 5% confidence level, those sorts of things, that question. Why 95%? Because it's arbitrary, isn't it?
It is kind of arbitrary. It's kind of like looking at that curve and saying, well,
exactly.
How can I get a still good result with a much smaller model? Right. So I think that's what goes on in the mind of a data science when they look at that and they say, yeah, Maybe I want to cut my model down by a factor of 2. Then I'll choose 200 dimensions and I'll get even better than 95% of the explained variance. Or maybe I can cut down to 150 and I still have 95% explained variance.
But this is where we would use some of the additional tools after the model is built, and it's part of the user interface that we're building in around this, like tensor boards, for instance, where we can move that threshold, alter the threshold manually, and it's sort of like a simulation graph, and you can see what it does to the overall model output on the test set, going all the way to however way the prediction is being used in the final consumption of it. Maybe that's like something that is presented to the user in an app, or maybe that prediction goes into the movement of a machine in a certain way.
Yeah.
And so the engineer, the data scientist or the data engineer, is arbitrarily picking that while turning their head going, okay, well, the output of this prediction is going to have this impact in the real world for me. Let me experiment.
Exactly. So the engineer is going to have a rubric or a metric that he or she has been given by his manager, by their managers. And they're going to say, we want this model to get, at least, let's say, we want to have at most 1% error in this model. And so then the engineer is going to tune this thing and make it as small as possible and still get that 1% error. That the management might say, we don't care if the error is lower than 1%. 1% is good enough. So the engineer is then going to go, okay, now I know what my accuracy has to be. Now let me see how fast and low memory I can make the application by reducing dimensionality. So that's like another optimization on top of that. So it's a constrained optimization. He's optimizing with the constraint that I've got to have it at least, let's see, not at least, but yeah, let's say at most 1% error. So he can go up to 1% error, and then he can tune everything else as long as he still stays at 1% error. Does that make sense?
Yep. Because that's what the business allows.
Yep. You have to do it with, like you said, you have to do that by paying attention to what the requirements of the task are. Okay. Then he talks about randomized PCA. I don't claim to understand this, but there is an implementation in scikit-learn, and apparently it's much faster. So in terms of computational complexity, it's dramatically faster. But he says when D, the dimensionality, is smaller than N. So D is the number of dimensions in the reduced feature set, and N is the number of, well, no, I'm a little bit, I'm talking off the top of my head here. D is the number of dimensions in the reduced data set, where, and N is what? M times N. N is the number of, N is the full feature dimensionality, and D is the reduced feature dimensionality. And he says when D is smaller than N, then randomized PCA is much faster, dramatically faster than full PCA. So I don't know this. I don't know why, the details of this, but Rachel had this class in numerical, what was it called?
Numerical algebra.
That's right, numerical linear algebra, right? And I think she covers that in there, these techniques with random matrices. That's really interesting to me. I just haven't had time to look it up. Okay, so that's that. And then incremental PCA, called IPCA, says you split the data set, the training set into mini batches, and you do this one mini batch at a time. Useful for applying for large training sets and applying PCA in an online manner that is on the fly as new instances arrive. Again, I don't understand this, but it's implemented in scikit-learn. So this is just kind of things to remember to have in your back pocket if you ever need them. I've never had to train a model in an online manner, that is with mini batches on the fly as they come in. I've never had to do that, but I know that's a common use case. And this technique, the technique of incremental PCA, is what you do, I guess. Okay, next is kernel PCA. I've seen this so many times, and each time I think I understand it, but I'm not quite sure that I really understand it. So, but he does give you a workflow to get this done, to actually use kernel PCA. He gives you a workflow in scikit-learn, so one can try it out, and maybe it'll work better than ordinary PCA. Anyway, so I'm just going to gloss over that. Then there's LLE, locally linear embeddings, which is another dimensionality reduction technique. I guess it's looking for a low dimensional, he's looking for like a linear nearest neighbor approach. Yeah, I'm not really sure about this. Yeah, I've read it before and I've kind of thought I understood it, but I really couldn't, I don't really understand it to the level where I can explain it. Although, again, scikit-learn gives you a workflow which allows you to do it. And then at the very end, he throws a whole bunch of other dimensionality reduction techniques out there and says about a sentence about each one. The only one I recognize is tsne. He talks about that. And it's used for visualization, I guess. When you have a high dimensional space and you want to visualize it by keeping the most important 2 dimensions. And then it guarantees that that if those 2 data points in the 2-dimensional space are close together, that means that they're also close together in the high dimensional space that you're mapping down from. Yeah, so that's, anybody want to say anything else about chapter 8?
I just wish I had more time to try it with not these generic data sets, but other data sets that I have that I'm intimately familiar with.
I think that figure 8.9 is kind of useful because it shows the it shows how the MNIST data set looks like if you compress it by preserving 95% of the variance. And I believe that is maybe, let's see, that might be related to figure 8.8, that graph, so that if we're using 400 dimensions to represent the MNIST data, and then we go down to 150 dimensions, we still get something that looks as good as the right-hand panel in figure 8.9. And, you know, just speaking for myself, I really don't see much of a difference between the original and the compressed. You know, my eye can't really pick out which one is better. So that sort of tells you what, it gives you a gut feeling for 95%, you know, for 95% of the variance situation. That maybe that's good enough that a human being couldn't tell the difference.
I totally agree. I like the KPCA with the RVF kernel. The reconstruction per image. If we go to the figure 8.11.
Yeah.
This kind of a reconstruction in a 3D space with the kernels compressing the feature space into the 2D and then projecting it back to the 3D dimensions. It's kind of this was the first time I came across this kind of a kernel and a hyperparameter minimization. And this is I love this stuff. So yeah.
Yeah, I love this stuff too. I mean, this is related to the kernel. The kernel trick that he talks about is actually from singular value decomposition. Sorry, not singular. Support vector machines. That's where the kernel trick comes from. And here he's applying it in PCA. And I mean, I can say the words, but I don't really have my head wrapped around it. What he does is he maps the problem into an infinite dimensional space that you can then map back to three, and then you can do something in that infinite dimensional space and solve some equation, and then you can map it back to the three-dimensional space. And it's very cheap computationally because you're using kernels, which are kind of like inner products, and it's very quick to compute an inner product, you know, because of vectorized, the machines all operate in a vectorized way now. That so taking the dot product of two high-dimensional vectors is very fast, if that makes sense.
Mm-hmm.
That's what a kernel is. It's a dot product.
Mm-hmm.
So you do some kind of operation, map the data into some infinite dimensional space, compute some kind of a dot product, and then map it back to, three-dimensional. Well, yeah. So I'm not exactly sure how computing the dot product in an infinite dimensional space would work, but it's supposed to be computationally cheap.
Yep. But there are also other stuff that are involved with respect to the plus I love the projection that goes around, and it sets it down to the 2D and then applies a PCA2 here to get the features, and then kind of so the workflow here, as you alluded to, that's a kind of interesting.
Yeah, and I'm also fascinated by the idea of reconstruction, where you embed or you encode an image and you mess it all up with noise and everything, but you force your network to still try to predict the original image, and in that way you can map an image to a much smaller number of bits. Like, you know, you can have a 200 by 200 image and map it down and encode it in maybe a few hundred values instead of, you know, the squared pixel array number of values. And then you add noise and mess it up and then force the network to still reconstruct something close to the original image. And that's kind of like an image compression technique, right? I'm not sure how JPEG and how JPEG works, but maybe it uses that or something. So yeah, this is the autoencoder kind of thing where you encode and then you sort of have a bottleneck where you encode an image down to a smaller number of features, and then you decode it back into the image, back into the same dimensionality as the image, and then you train the network to consistently produce an output that looks like the input. You know, you can calculate the reconstruction error, and that would be your loss. That could be related to your loss function. And then that way you can train the network to reproduce something close to the input image, no matter how, well, of course, it's not going to work if you put in too much noise, but by throwing in noise and forcing it to still perform, you're kind of regularizing it and making it more robust and more generalizable.
Mm-hmm.
So I was thinking that, what if you have, so we've read about where you take a whole bunch of images and do that, a big data set, a training set of images, and then you train the encoder in such a way that it can compactly encode each image. so that it knows how to do that. It compactly encode the image such that when it gets decoded back up to the size of the original image, it produces something that agrees with the original image. It's not too much different, right? That's the autoencoder. But so that in that way, an autoencoder can compress an image, because the encoded representation of the image can be considered as the compressed image, right? Once you train the network to do that, then you can give it any image as an input, and it will produce an encoding of that image, which you can then send to your friend or whatever, and that way you're sending your friend a compressed image, and then you can send your friend the decoder, and then he or she can decode it and blow it back up to the original image, or at least something closely resembling it, right? So that's image compression. So I was thinking, what if you have only like one image, and then how could you train an autoencoder based on one image? So you have one image and you try to make it an image that has lots of different scales in it, right? Maybe, I don't know, something that has like flowers and plants and things at all different scales, objects at all different scales in it. And then you train, and then you take that image and you pollute it with, you make many copies of that image, many noisy copies of that image, and use that as your training set. And then you try to train a network to give you back the image, the original image. And then I'm wondering if you take that network that was trained on only one image, would that be like a pre-trained network that you could use for other data sets? Kind of like using transfer learning to make that apply to other data sets?
Yep, the prior will be based on the image that we have selected.
Yeah, yeah.
And it depends upon the generalization factor too, because those textures and those how well that texture will be, if we talk about the feature level, this one image that the deep neural network has learned, the generalization aspect will be very narrow.
Yeah.
And kind of a then if we want to transfer it, that will be kind of a style transfer approach, in which
Yeah.
the style of a particular uh, image needs to be embedded over the second image based on the
Yeah.
texture representation and the shapes that it learns.
Yeah, you're making a really good point about textures and so on. What I was, so that you're limited, your generalization will be narrow in terms of textures. But what I was thinking of is, if you have your initial image sufficiently representative of what do you call this, composition at all different scales, compositionality at all different scales, you know, from like 5 by 5 pixels to 7 by 7 pixels to 20 by 20 pixels, the structures at all to have in it structures at all different scales, like little insects, flower petals, stems and buds, things of all different kinds of scales, as many as you can, and get into this picture. Then at least the CNN part of it should be generalizable. In other words, the part that looks for patterns at different sizes, that part should be generalizable. And you know, and it should work at least somewhat right out of the box. But then you would have to, like you said, you would have to train, just like in transfer learning, you'd have to train the later levels of that network for your specific data set that you wanted to apply it to.
Yep. Here we might apply an LDA2, a linear discriminative analysis-based technique, in which, based on the feature sets at a particular layer, we might also try to classify it. Suppose if one image has a metal and a insect and other stuff too, then we might try to extract it firstly by trying to get a kind of a manual if we are just doing on a single image, and then manual algorithm that tries to come up with those features that can be extracted, and then to generalize it to we might have to apply some sort of distributions that or some kind of a probability at sixth or a seventh layer, or if we are taking CNN backbone for example, and then try to extract those features based on the representations that we see are necessary, but that will have some sort of a hard coding or causal relationships that can be applied. But I don't know. From a computational point of view, can that be extended, or uh, uh, that particular feature that we are trying to get? Uh, uh, if it's a kind of a style transfer, then that will work. But if we are trying to apply that manually in a particular feature selection space, like in R, uh, that we write uh, 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 we used to do in classical sense, the R-based methods. Uh, that based on the distances and the uh, features that we manually needed to select. But I don't know. I'm all over the place.
No, I think you're right at that. What I'm thinking of is maybe more suitable for a cell transfer approach. I was just sort of wondering, like, wondering if there's any benefit in using a small, maybe just single image. Single image is maybe too small of a data set, but maybe a very small number of images to train a network that knows how to compress images, and then use that encoder as kind of like a pre-trained network to start working on a new data set. In other words, if you have a large data set with thousands of images, and you have to train that from scratch, then, well, but then the other thing is you don't have to train it from scratch because you can always use ImageNet. Oh, well, so that's probably not. Anyway, let's move on to chapter 9. Sorry about that.
No, it's fine. It was a good elaboration, yeah.
So anybody want to talk about chapter 9?
It starts with the Jan's famous comment regarding if intelligence was a cake, the unsupervised learning be the cake, supervised learning will be the icing on the cake, and the reinforcement learning will be a cherry on the cake. So, yeah.
The thing that is most attractive to me about this chapter is that it provides methods for anomaly detection, which is an important problem in industry, I think. There's a lot of things a lot of applications in industry for anomaly detection and not only in industry, but in science as well. For example, earthquake detection, looking at seismic waves and trying to predict when there will be an earthquake. That's an important problem. And another problem is like fault detection in, say, if you look at a VLSI circuit, I know Srinivas is an expert on this, you can have a neural network analyze images of VLSI, microscopic images of VLSI or highly magnified images of VLSI circuitry and try to detect where the flaws are. And it's important to understand the processing yield for these things. And so that kind of an anomaly detection model would be really valuable.
How does unsupervised then relate to Jan LeCun's idea of semi-supervised?
I guess semi-supervised is when you're able to make something work that you would have normally thought required a huge number of a huge training set, but instead you have a small training set, but you figure out how to make it work only with those small training examples. And I think one example that we've already seen in this textbook is I forget which chapter this is in. It was the autoencoder chapter, where you start with your small images and then you train an autoencoder. And then you get the, let's see, maybe this is exactly what I was thinking of before. You start with a small number of images and you train an autoencoder to compress them or encode them. And then what do you do?
A good example of a semi-supervised is language models, where you can use the next word or the next character, and you have the teacher forcing kind of stuff. So the data itself provides you some level of supervision to be able to predict the next instance or the next portion of the video and stuff like that. Whereas in the clustering algorithms, there's absolutely nothing which tells you how to cluster them. So those are totally unsupervised.
Right. So there's self-supervised. So what you've described is self-supervised. But isn't there another class which is kind of like, in other words, you have all the labels. Self-supervised means you already have all the labels that you need. But there's another one, semi-supervised, where you start with a small set of examples and somehow you're able to make it work. And I think that's where all the buzz is now, the semi-supervised learning area, which I don't really understand very well.
Which should be right before dbScan.
Let's see, dbScan is all, where's that?
Yeah, so page on the book, page 253.
Okay, 253.
Using clustering for semi-supervised learning. When we have plenty of unlabeled instances and very few labeled instances. So let's train this logistic regression model with 50 labeled instances, and you've got it, blah. And then the accuracy is what it is. Now let's see what we can do. First, cluster the training set into 50 clusters. And then for each cluster, let's find the image closest to the centroid, and we'll call those the representative images. And there you got that. Then let's look at each image and manually label it. Now we have a data set with just 50 labeled instances instead of being random instances. Like the
oh, so these are like golden examples or whatever. So in some sense, they're better value, they're more valuable or give more information.
Is this what in Silicon Valley, everyone talks about this back in like maybe 5 years ago or so, they were doing all the image recognition. And so they just needed to label a handful of images, cat pictures or whatever. Private parts of people just being labeled manually. So that was just enough to get that representative sample, and the models would then be able to pick up any and all.
But what we were told is that, you know, you need thousands to 10,000s of examples for a good neural network model. That's what I remember being told.
Well, that's why you have Mechanical Turk, those Amazon Mechanical Turk, where you hire people for like every image for every 10 images they do, you get a cent. It was great for using cheap Filipino labor or Indian labor and so on.
Yeah, this is a little different, right? And also this goes along with what Andrew Ng has been saying in his talks. He's saying that you know, in the old line of thinking is that you need 1,000 to 10,000 images to have a good model. But he said that's only if your images, if your training data is poor quality. If you can increase the quality of your training data, then you can accomplish the same, you can make a model that's just that has the same accuracy as one with 10,000 images with many fewer images. If you somehow can identify those images that are providing the most information, the cleanest ones. Remember his talk, that's what he's been saying. I heard a talk by him last week, and that's what he was saying is that if you clean up your data, that's, in other words, the ML ops centric way of thinking is leave your models alone. Don't try to tweak them up. Just focus on the data and see if you can clean it up. And he said that by that approach, you can often get great improvements in your accuracy by giving the model cleaner data. And that's what he's doing here. He's saying, all right, we've got 50 labeled instances that somebody told us about. But instead of using those, let's, like you said, you were walking through this, let's look for 50 clusters and find the best example of each cluster. So that way, in that sense, you're getting better examples than the original 50 that you started with. And then when you run the model, he finds a terrific improvement from 83% to 92%. And it did require a little bit of human intervention, right? You had to have a human get in there and label those 50 examples.
Yep. Human, we call it human in the loop.
Human in the loop, yeah, human in the loop. But this is great. This is great that you called attention to this, because a lot of times you read this stuff and you sort of are amazed when you read it. I remember, I always mark up my books, and for this one, I wrote a lot of stuff down that it was so amazingly great, and then I forgot all about it until you brought it up.
Well, it was just that Maya mentioned something that sparked memory from Jan LeCun. But the philosophical idea here is variance, how much of the variance is captured by those representative samples, representative labeled samples. And the Andrew Ning's point, if you pick the right representative sample, that gives you what you need. It just seems very intuitive when you think about it. But but at the same time, how do you make it practical? How do you really know that you're getting that right? You've made that right sample pick.
Yeah.
What's a metric here? Do you construct a metric of your own to say this is how we decide that we did pick the right sample? And it's just basically you're going to be, we're talking about certain image data here, but say you weren't using an MNIST image data, you're really using your own subject matter's data. So you're going to have to come up with some kind of a metric to say this kind of performance is what we're looking for the representative sample.
Yeah, I mean, in this case, he says, all right, we've got 50 instances, let's look for 50 clusters, but that's arbitrary.
Exactly.
You might look at the data and see that it only makes sense to look for 20 clusters, you know, and then you might decide to restart again. And I'm looking at how he, you know, the first thing that you went through on page 253 is only his first idea, is only Jeroen's first idea. Then he says, let's make it better by doing this thing called label propagation. Yeah. So he says, take these clusters, these new 50 clusters, and take the human labels that we found for each representative instance and propagate those labels throughout the entire cluster. So now we have a training set that that has not 50 data points, but it has thousands of data points.
I applied this in a project I did for one of the big insurance companies, healthcare insurance companies in the US. The color was blue. Everyone knows it. And so in order to break out and figure out what was the ideal number of clusters, it was really conversations with the medical professionals in that insurance company, sort of like part of the CMO, a chief medical officer group. And they said, okay, so we're looking at the Medicare patient population. And so you have men and women. So let's discuss who these people are generically. There were week old ladies, and really we call that group week old ladies because these are female patients above the age of 65 who have osteoporosis.
Yeah, that's it.
We had fat smokers. These were elderly men who smoked and their weight was above it. And literally, we pegged it that way and gave us the count that we felt that when we did the agglomerative clustering, we're able to get the right clusters of patients, members, and then build predictive models of what we specifically needed for them based on trying to predict readmissions and all that.
Yeah, so that means applying domain knowledge to figuring out the right number of clusters.
Exactly. It was trying to get into something like this because, yeah.
So this label propagation method gave him another improvement of from 92.2% up to 93.3%. He says, that's not so great. Let's see if we can make that even better. And he says, maybe the reason why this didn't work so well is because we propagated the labels all the way out to the boundaries of the clusters. And you might imagine that at the boundaries of the clusters, there's confusion between whether a thing is belong to this cluster or whether it belongs to the next cluster, right? At the cluster boundaries, you're not so sure about membership, about cluster membership, right? So he says, let's try the label propagation, but not all the way out to the edge, not all the way out to the end of the cluster. And when he did that, he said, let's propagate the labels only to the 20% of the instances that are closest to the centroids. So instead of applying it to all the data, you only apply it to the selected 20%. And then he gets an improvement up to 94%. So that's pretty cool. I thought that was really cool.
90, that's the active learning part.
Well, it's label propagation, but then it's sort of like, how would you say it? Intelligent label propagation, not just blind label propagation. So he says, he summarizes by saying, with just 50 labeled instances, only 5 examples per class on average, because there's 10 digits, we got 94% accuracy, which is pretty close to the performance of logistic regression on the entire data set, which is roughly 97%. So he says this good performance is due to the fact that the propagated labels are actually pretty good.
Yeah. i.e., the representative samples that you picked were pretty good. You're lucky.
So this is an example of what Andrew Ng was saying, is that by cleaning your data, you can get better results. You can improve your results without even changing your model.
Yep. This was a paper that recently came out. It's a Sentry named Selective Entropy Optimization for Unsupervised on Domain Adaptation, and in which that shift in those clusters based on the label that we select, it kind of optimizes it. And the stuff that Mash just talked about with respect to having some kind of a adaptation so that your errors are not accumulated, such that your active representation sample is correct to have that approach for self-supervised classification. This was a paper that I recently came across. Oh, sorry, the semi-supervised classification.
Mhm.
Yeah. So
Let's see. So is there an interesting that he talks about the MNIST? They talk about one of the data sets they've applied this method to is the MNIST data, but is there like a brief, is there an explanation of the technique somewhere, or maybe maybe the abstract is good.
In the abstract, halfway through, our algorithm then selectively minimizes predictive entropy to increase confidence on highly consistent target instances, while maximizing predictive entropy to reduce confidence on highly inconsistent ones. Basically, they're splitting. They're splitting the data set based on this notion of predictive entropy. That's the metric.
State of the art. So he's trying to get they are trying to get accuracy on when the domain shifts. In other words, they train a model on one data set, and then they try to generalize it to another data set that has changed or something. That's what they mean by domain shift. I recognize that term. So apparently they're trying to develop methods that are more robust when you go from one domain to another. I guess you would say distribution of examples to another. Standard UDA benchmark. What's a UDA benchmark? A UDA algorithm.
Unsupervised domain adaptation.
Oh, there's a cat outside. Oh, hold on for a second. You guys go ahead. I'm just gonna go look into this.
Yeah, our cats have to stay in the front yard and the dogs stay in the backyard, because when they mix,
Yep. So this was distribution matching via the domain adversarial learning. Based on that domain, we shift.
Did these guys at Georgia Tech present this at the big deep learning conference?
No, this was presented in there's a weekly lecture series by Matthias. He is a professor for visual computing and artificial intelligence at the TU München. That's university in Germany. So
That's another one.
Just the link to this profile. So, this is a series of lectures that happened. Yeah, I came across this from. Other than that, the clustering for pre-processing tasks that here they do with the k-means as a pre-processing step. Here, the data set dimensionality that they so they go on from 64 to 50 and then try to perform the best domain that they select based on the cross validation. This is from the book. I'm discussing the 9th chapter from the book, which is underneath the using clustering from for pre-processing, which is done here manually. And the pipeline using the k-means and the log regression. And then he finds the grid search CV for the optimal number of clusters that we get. Then under the heading using clusters for semi-supervised learning,
I went to this Twitter guy. I went to Neisner's Twitter site. Is it there, or is that what you're sharing?
Yep, he is a professor for visual computing and artificial intelligence. He does a weekly lecture series, AI, in which he discusses the different uh, uh, vision, state-of-the-art methodologies and other approaches that are currently, it's basically research oriented, but yeah, it's cool. And I
Is
got
there a
the
link to his talks? Is there a link to his weekly talks?
weekly talks.
Yeah, YouTube.
Oh, you find it on YouTube?
Go to his
Yeah.
YouTube channel.
Yeah, I will put that here too.
And subscribe.
Nice. This here. It's not.
Yep.
Good God, he gets all the like just researchers. This is how you keep up with
Yep.
cutting edge research, which is hard to do.
Yeah.
Because if I go and read a research paper and without a context and some priors about the how that thing came into picture, that that context with respect to that stuff is important, in which you get to have kind of information with respect to the uh, continuous stuff that's being taken from the continuous stuff with respect to the things that are currently happening uh, in the world with respect to that particular topic that needs to be taken care of, which he taken care of in the sense of uh, within that subsection of a particular topic, what are the uh, 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 neighboring or the state of the art research that is goes around, and plus Sam also had a, I don't know the podcast. He also talks about this kind of stuff, and sometimes on the research uh, guys that he invites. So yeah,
Yeah. This is interesting.
So we were discussing the clustering for semi-supervised learning and how we can have that same clusters here. Now let's change the model again on a partially propagated data set. Yeah, and this also had an effect on the active learning. Uh, uh, the labels that we initially selected, and the estimated probability of the lowest X argument to the expert to be labeled here. But that's not always the case. This kind of problem that happens all the time. Uh, yeah, because it depends upon the data set and the distribution of that particular class samples that it has. This it they give an example to how to correct these shifts. Those labeling errors, those shifts in which your data is scarce, and yeah, a couple of other things too.
So he talks about an iterative process of active learning where you select a random sample of labeled instances. Sorry, I guess you have a sample of labeled instances, and then you label all the unlabeled instances. You predict on all the unlabeled instances using a model trained on what you had, and then among those labeled instances, among those predictions, you look at the ones for which the model was least sure of its result. And then you say, okay, those are the ones we need to label. So then you have the next round, you pick a sample of those, label them with humans in the loop, and then repeat. And then see if you got better results. And then again, you take the ones that are the least certain, the predictions that are least certain, the examples for which the predictions are the least certain, and have them labeled by humans, and then rinse and repeat. And then at some point, you don't get any more improvement, or you get the improvement you get isn't worth all the human effort of labeling, and then you stop. So that's a description of the active learning, of one implementation of active learning, I thought.
Next, we move on to DB-scan, the clustering that happens with respect to the sklearn neighbors. The sklearn API using the k-nearest classifiers that they took. It's the make moons data set, the kind of a DB-scan clustering that they have they have used here. And the DB-scan class, this algorithm works well if the clusters are dense enough and if they are well separated by a low density regions. So yeah, this is the prerequisite for using DB-scan. Then they gave a simple example of using this. there is a hierarchical DB scan too, which is in the scikit-learn contrib project. Yeah, we can use that too. But the complexity is roughly, I think so, it's order of m log n, which is pretty much linear with regards to the number of instances. Uh, so
So I guess this is a way, I guess he also says it works best when the clusters have similar densities, that if there's lots of different densities, then if the clusters have different densities, then you're in trouble with this method. And he also says that it's good for anomaly detection because it actually labels examples that aren't in the cluster. It labels them as anomalies.
You just said it. Density matters. So anomaly would be anything where the density is no longer as uniform as the rest.
Well, an example that lies outside, it actually tries to think of continuously connected regions so that have the same density, right? So it finds, like in this half moon problem on figure 9.14, if something lies outside of that, of one of those half moons, then it's labeled as an anomaly. But as you said, it's in a lower density area. It's in a lower density region, so it's not part of the clusters that it identifies. But I guess that's tunable too. I mean, you have some control over how, over whether how strict it is about classifying anomalies.
Yeah,
But there's
based on
only
the
two parameters.
distance. Yeah.
Yeah, there's only two parameters. You get what is it, epsilon and two hyperparameters, epsilon and min samples. Where what's epsilon?
Epsilon will be the I think so, the distance between the two instances of the clusters.
And
I think so that's the decision boundary that, yeah.
And then min samples must be the minimum number of samples in a cluster or something like that.
Yeah, it
I'm not
seems
sure.
like it.
I'm not sure what that is.
Even I have forgotten at a particular time. Epsilon is 0.05 dp scan. But anyways, we can take a look at it in the documentation.
And then there's k-means, which is a really interesting and an interesting algorithm that is well known, and at least data scientists are supposed to know it well. And that's where you decide how many clusters you want, and then iteratively find the centers of the clusters. Let's see. I think you have to specify the number of clusters you want to start with, and then you randomly select. Say if you want 5 clusters, then you randomly select 5 points and say, okay, these are the centers of the clusters. Then you calculate the total distance of all the points from. Let's see. Somehow you. Let's see. The iterative step is you try to adjust the centroids, those 5 centroids, to minimize some kind of a distance measure. Yeah, so initially you just randomly select the centroids, and then you iteratively improve until you've got the best possible values of the centroids. And as far as the precise algorithm, He talks about that here. Figure 9.4. Yeah, it's figure 9.4 shows the iterative steps leading to the final 5 centroids. So let's see.
That's a k-means.
Yeah. I thought it was supposed to be random. Yeah, initialize randomly, top left. So you just choose 5 random points. You say, I want 5 clusters, so I choose 5 random points anywhere in the data set. Then what do you do next? You label all the instances that are closest to each one of the centroids. How do you do that though?
I think so that average of a particular cluster is first on decision boundaries are made, then a average of
Yeah,
a
you have
particular
this
cluster.
Voronoi tessellation thing where you make the decision boundaries. Not clear how to do that, but and then you just iteratively update, and the algorithm is guaranteed to converge in a finite number of steps, usually quite small, but it will not oscillate forever. So, so that sounds like a pretty cool algorithm. And but then there's still the decision you have to make is what, how many clusters should you ask for, and that requires human intervention.
Yeah.
Oh, and then as a warning, it says that although the algorithm is guaranteed to converge, it may not converge to the right solution. It may converge to a local optimum. That's not good. So I guess to make sure that you didn't get tricked into accepting a local minimum, you run the algorithm several times, initializing it with different random set of 5 points, and then see where it converges. And then, you know, let's say you run 10 of them, and then you find that, yeah, 8 of them converge to the same solution, and the other 2 are converge to something else. And then you can say, oh, you know, I'll avoid the local optimum by choosing one of these 8 solutions, or the average of the 8 solutions.
And then there was the center k-means plus plus algorithm too, which had a smarter initialization step.
Which one is that?
K-means plus plus.
K-means plus
Just
plus.
just beneath on the heading centroid initialization methods, just after the 9.4 figure. 9.5, the suboptimal solutions, and he discusses about the k-means plus plus.
K-means plus plus.
A smarter initialization step that tends to select the centroids that are distant from one another, and it makes the k-means algorithm. Yeah, I haven't read the research paper yet, but yeah, this seems like an interesting approach to arbitrarily initialize the clusters. But for the initialization too, we might have to take a center and then choose uniformly at that space, and then from that distribution, that probabilistic distribution, we might have to set a minimum distance that I think so. It uses go into the details of this algorithm. We might have to uh, get to the research paper, but that's for some other time.
And he says that's the one, the k-means plus plus that you pointed to is the one that scikit-learn implements. When you ask for k-means, that's what you're getting. So that's good to know.
Yeah. Then they they get to accelerated k-means and mini batch k-means. This was another improvement.
Yeah, the mini
Variant.
batch is interesting because it allows you to do big data sets it allows you to find the cluster centroids for data sets that don't fit in memory.
Mhm.
So, and it's also faster, so that's pretty good.
Yeah, because applying a PC and then incrementally trying to map those latent spaces, yeah, that might be that inertia is generally worse. I think so. If you do it at the incremental PC at each step, at each mini batch at a time, uh, because you will need to perform multiple initializations, then take the best, and then try to. That's one reason too. Uh, so,
Finding the optimal number of clusters. So he gives a technique for finding the optimal number of clusters by calculating this inertia term and looking for the elbow.
Which he does quite well in the exercise problem with the Olivetti faces.
Oh, okay.
Yeah.
Olivetti faces problem.
Cluster the Olivetti faces data set, question numbers 10. Now it doesn't, when you try to use the inertia approach, it doesn't give you a perfect elbow to pick the right number of clusters. So you just sort of, you can't arbitrarily go, all right, I'll go with 100. And then he says, okay, now that you've done this, so let's look at what these images are by these clusters, and you can.
So he also gives a more precise approach. He calls it the silhouette score. That he says that after he introduces this inertia term thing, he then says that's a pretty coarse method of choosing the right number of clusters, and a better approach, but more computationally expensive, is the silhouette score. And there, figure 9.9 shows how to find, I guess, the maximum silhouette score is what you're looking for. And so by doing this in this problem, I'm not sure which data set he's using here, but he finds there's a maximum at k equals 4. So there's a principled way to choose the right number of clusters. It's not just arbitrary if you're willing to put in the extra compute time. So that's all good to review. Then he shows that k-means is limited if the clusters have weird shapes. Notice that the examples in which the cluster k-means worked well were the clusters look like they're all circular, have a circular footprint. But then in figure 9.11, he says that, well, in these they have elliptical footprints. Well, some of them have elliptical footprints and some of them have maybe circular footprints. And in this case, they don't, the clustering doesn't do a good job. But he says that another method called Gaussian mixture models does work well for this case when you have the clusters that have elliptical footprints. So the elliptical footprint is characterized by, the shape of the ellipse as well as the orientation of the ellipse. And in a most general case, you could have ellipses of different, I guess it would be three things: the size of the ellipse, the shape of the ellipse, and the orientation of the ellipse. And Gaussian mixture models can handle all three of these things. So it's a much more general way of doing the same thing, of clustering the, selecting the right clusters for the data. And the Gaussian mixtures is also done by an iterative process. And I think it's discussed maybe somewhere else in the book. It's not discussed here. Clustering, clustering.
For anomaly detection, I think so. These are the number of
Anomaly
clusters.
detection.
Yeah, the Gaussian mixture models for anomaly detection.
Oh, he does talk about Gaussian mixtures at the end of this chapter. Yeah. Yeah, and then, like you said, there's a chapter on anomaly detection using. There's a section, anomaly detection using Gaussian mixtures, and then there's a different principled way to select the number of clusters using the Bayesian information criterion or the Akai-Ike information criterion. Let's see there. But does he talk about the technique of solving the Gaussian mixture model? He shows how it's implemented in scikit-learn, but it doesn't look like he shows the technique. Oh, expectation maximization. That's the algorithm that's used, and I think he talks about it on page 262.
Yep.
I've read through this. Yeah, go ahead.
Sorry. Yeah, the figure 9.16 it represents the same. I think so. Yep. It's a form of expectation minimization in which those categorical distributions are taken. Even I have, if my memory serves it right, then these the EM algorithm is similar in much way to the k-means.
Yeah. Yeah, it just introduces like the K. I think it's exactly equivalent to the k-means in the case when all the clusters are circular or spherical in higher dimensions.
Yeah. Plus the density contours that it makes and the decision boundaries that it selects based upon that is the distances between those Gaussian distributions based upon that decision boundaries. That's refined iteratively, as you have alluded to. But yeah, this also helps in the kind of approaches where you have one multiple uh, selection criteria of a number of features that can be used. I think so. This is very much useful in a kind of handwriting prediction, and it can also be modeled on the the other vision tasks such as fraud detection, uh, and then the anomalies kick in, and yeah, we can use that as a fraud, the removing outliers in the data before the training and other stuff too. And then that will, I think so, make a good point because we have multi Gaussian models, and those, if we train it in a low data regime, that might have some sort of a uh, uh, positive effect on the domain adaptation. Uh, if but yeah, that of course will uh, have the same problems. But this might be good with respect to the distribution that we see and the interpretability of it, because we can see the contour maps that are represented, and uh, yeah, that was my.
And then he talks about Bayesian Gaussian mixture models where the model chooses the number of clusters. So it's an even more principled way to get at the answer, to get at the best model. So you have to use some prior knowledge when you set the initial value of n components. You have to have some reason, some principled reason to believe that it's close to, whatever you set it to be, like, 3 or 4 or whatever. Greater. Oh, and it says set the number of clusters to a value that you have good reason to believe is greater than the optimal number of clusters. And then the algorithm then automatically finds the right number if you've done that properly.
Yeah, but
So
how will the algorithm look at the uh, number of Gaussians that are optimal for a particular problem that we need to approach? I mean, it won't be able to detect the features like we do it in a PCA, for instance. Uh, yeah, but we might have some kind of a maximum likelihood approach in which we, yeah, that can be done using a kind of a maximum likelihood in which we try to weigh our mixture models uh, to detect the number of Gaussian instances that it needs to be initialized with, the number of components here. Yeah, that makes sense.
well, he has the mixture model in figure 922. And I'm not, I mean, the question you asked is the one that is the right one. I mean, is how do they do that? How do they select the right number of clusters? And I think by sampling over, over numbers that are, so you choose 10, let's say in this problem, you choose 10 as the maximum number. So then it just says, okay, well, we'll sample 9, 8, 7, 6. We'll sample all the different possibilities and we'll come up with the one that has the best model. So but I'm not sure where in this model on figure 922, I'm not sure where they sample over the number of clusters.
I don't think so. They do here. I think so. For that, we might have to use a hyperparameter selection approach to kind of tune our model to select the number of components that best represents the end-to-end requirements of a particular threshold, or the more importantly, the latency and the inference speed that we require.
No, but
Because
this method does, he says that this method, this algorithm automatically figures out the right number of clusters. So you don't have to, there's no, it's a hands-off approach. You just set it go, you just set the model going, and then it figures out the right number of clusters to include. So I'm just trying to see where in this model it's sampling over the number of clusters. I don't see it right now.
But this is interesting.
Yeah, it is. I think this is one of the most interesting topics in the whole book, is this last piece on Bayesian Gaussian mixture models.
Mhm.
Anyway, that might be a good place to stop.
Yep.
Late 8. So we just basically finished 2 chapters, but that's good enough, I think.
Mhm. Yeah, because there are too many things that the nitty-gritty of the stuff that we need to discuss.
This was a great course. There are so many levels that you can study it at. I mean, there's each chapter has lots of material and lots of deep material in it. So, one approach could be just to cover the basics, the core material, figure out what the core material of each chapter is. And then the second level would be studying all the material. And then the third level would be to actually read all the papers that he references, because every chapter he references at least half a dozen to a dozen papers that are interesting. And it would be great to study it at the third level, but there's not time to do that. But I think it's a terrific reference book, because once you've been through it, you kind of know where all the bodies are buried, right? And then when you have a problem to solve, you just come back up, you look in the table of contents and figure out which sections you need to refer to, and there you are. It gives you the methods and refreshes your memory on them. So anyway, it's been a great course. I'm so glad we did this. I think we started back in July, maybe. I don't remember. Yeah, it's been a long journey here.
I want to say it was May when we started.
May, was it May? Wow. So it's almost a year. But it's an 800-page book, so more than 800. Yeah, 800 pages. Anyway, I'm really glad to have done this, and I'm glad that we all completed it together.
Yep.
So yeah, and 2 more courses coming up. One is on Sundays. We're going to start the reinforcement learning class. I know that Mayank is excited about that. Not this Sunday, but next Sunday, because this Sunday's Easter, right? So April 11th is the first day. It's going to be the same time slot that we've been using, except the 10 o'clock time slot, except it'll only be once per week. And then the second course is going to take the Wednesday night time slot, this time slot, and that's the one that Wenchang is going to do on machine learning in production. And I think Mosh is working with Wenchang on that. So that's exciting too. Yeah.
We are, but we certainly need everyone's help.
Yeah.
What would be useful if Srinivas and Rekil and others who've been active also jump in and take certain chapters, especially.
Definitely. Yeah, definitely. Well, Wenchang has yet to put out a plan, a schedule. So when he does that, then we can all have a look at that and see which parts we can jump in.
I'll ping him in the morning. Yeah.
Yeah, I've pinged him about this, and he's been very responsive. He says he's going to get it done soon, but he hasn't got it yet. So
Yeah. So he, I got him 2 engagements,
Mhm.
Projects,
Mhm.
and so he's got work.
he's busy. Okay. Okay.
Well, he will do it. He's always working.
He's very conscientious. Yeah. All right. Well, I guess the next time we'll see you is at that kickoff meeting next Wednesday.
Yep.
Hey, Mash, I sent you a message.
Uh-huh.
So I see you weren't offline. I just want you to catch it before you hang up.
Why did I not see it? It didn't show up.
Because your notifications are off. So
Can you send it to me by email? I'm putting my email,
sure, yeah, absolutely.
and this is the same email address if you want to connect with me on LinkedIn.
Awesome. Okay, we'll do.
All right. Okay, Terrence.
Let's see. I just want to make sure, Masha, are we connected? I know Mike
Oh,
and I are going to collect. Are we connect? And I know I'm connected with Yuri, I think, and I'm not sure about Srinivas, but Terrence and you, I think we're connected, right?
Mm-hmm.
All right.
All right.
I'll connect.
Joseph, I follow you all the time.
Oh, okay.
Stuff. But Srinivas, I'm not connected with Srinivas at all.
Okay. Let's see if we can find Srinivas on LinkedIn.
Srinivas, I think I asked you once, and I don't think did you say you didn't have a LinkedIn?
I do.
Oh, what is it, Srinivas?
I think it's Srinivas Raman,
Raman. Okay.
Raman.
Srinivas K. Raman. Is that it?
Yep.
Oh, okay. There's a Srinivas. There's a whole bunch of Srinivas Ramans, but there's one Srinivas K. Raman.
Yep.
That's you. Okay, great.
I didn't want to say Srinivas Raman. That's going to be hard. How do we know that's you?
Yeah, Srinivas K. Raman and San Francisco Bay Area. Is that the right one?
Yeah, let me check. That should be me.
Okay. Penn State University. Is that?
Yep. Yeah.
Okay.
That's me.
Okay, that's the one. All right. Great. And then Yuri, what's your LinkedIn?
Looking for.
Yeah, and mine is my name as well.
Terrence Rideau. Okay,
Yes.
I'll look for that.
Everybody uses LinkedIn now. That's the new social network that no matter where you go, you have to have it. I gotta clean mine up.
And what's nice about it is they don't make you take the paid version. So, you can do perfectly fine with the free version.
That is correct for a reason. So Microsoft owns it, and it is integral to the overall product strategy for all the.
Oh, I didn't realize that Microsoft owns that.
Oh yeah.
Recent or?
Several years now. It's essential, and it's also used by Salesforce. It is how if you don't have a LinkedIn, you're not working.
I found Yuri on the first try because I don't think there's more than one Yuri Schlachter name. So I think that's the one, right?
Yeah, probably.
A GRO Intelligence, GRO Intelligence. Yep. Is that it? Okay, got it. And you're Penn State also. Interesting. Yep. Okay, I was already connected to you, so that's good. So now I'm connected with Srinivas, Terrence. Well, I've got a connection request to Terrence. I'm already connected to Yuri. Masha, I think I'm connected already. Yeah, and then Mayank, I think I should just get yours.
Mayank is always very active on Twitter.
Mayank, what's Mayank BHA? What's your last name, Mayank? BHA something, I don't know. Okay.
BHASKAR. Sorry, I was muted.
BHASKAR. Okay, great. Mike Baskar. There's a bunch of those. Okay, I see it. It's the same. It's the same picture that you have. Yeah.
Yeah.
Okay, I got that one. So I'm going to send you a connection request. All right. Okay, gentlemen. Anything else before we unconvene? All right, then. Good night, everyone. Well, for some of us, good night. Good morning. To have a nice day to Maya, because it's already morning. And yeah, we'll see you next Wednesday.
Thank you.
All right. Thank you.
Bye, everyone.
Bye.
Bye.
Thank you, everyone.